Hello Calc, it's Wednesday the 15th, and eventually we're going to be studying the area between a curve and the x-axis, but before that I want to mention that these topics will be covered on your first Math League test, which I think is Friday. So they are limits and continuity. The limits are one-sided and two-sided. So remember, the limit as you come from the left, the limit as you come from the right are one-sided, and the limit as you approach a value is two-sided. Derivatives and tangent lines. How do you take a line, a curve, and find the equation of the tangent line? Velocity and acceleration, and implicit differentiation. Another topic coming out of derivatives is the chain rule, and I do wonder if I presented it the way, this way. Did I ever say to you the derivative of a function inside of a function is when you use the chain rule? I probably did. But in general, we're going to take the derivative of the outside function. So we're going to have the derivative of that thing we called something inside, followed by the derivative of that something. So this is what I called something. So let's be a little more mathematically prudent and call it f prime of the inner function g of x times the derivative of that inner function. So for example, in this one, the sine of x cubed is the cosine of x cubed followed by the derivative of x cubed. Alright, so I just wanted to show you that notation that might help you through on one of the questions. So studying these topics and this little reminder about the chain rule. Alright, Matt, are you out there?
Yeah.
Can you give me a paper towel? Alright, so good luck on that Friday work, and I'll let you know for sure what whether that's happening this Friday or the next. I can't quite remember, and I will get you that information. Alright. We've only got about 6 topics left for the rest of this year. And these 6 topics I'll present fairly quickly so that we can spend some time practicing AP questions. Whether we take it or not, it's like a way we can pull all of the thought together at once, and it really gels it. So one of the topics I want to add to, we actually have alluded to and used to some degree, is the area between a curve and the x-axis. So I'm going to show you that, first of all, with a little picture. So suppose I have the sketch of a function, and part of it is going to go below the x-axis, some part of it's above, and another part's below, like that. So if I call this part A, and this spot B, and the function f of x, can you remind me what the integral from a to b of f of x will tell you? The answer is, the integral will take all this area and call it negative, and all this area and call it negative. Anything underneath the curve, by integration, will become out as a negative value. And then it'll take the area above and call it positive. So say this area is big A, big B, and big C. So then this will give us the area of A, which will be a negative number, plus the area of B, and plus the area of C, which will be a negative number. So sometimes it's necessary to find the integral, and it depends what the question and circumstance is, and what the circumstances are. But I want you to be aware that a straightforward integral is always going to calculate this as negative, and sometimes you don't want it to. So let's talk about when you don't want it to. Suppose you wanted to know the area between a curve and the x-axis. So you want this area to be positive, this area to be positive, and this area. So what you would have to do is divide this into 3 integrals. So say this part, we have A and B, say this crosses the x-axis at C and D. So we're going to have to take that first spot, we're going to have to find where this curve crosses the x-axis. And we're going to have to, I can see on mine, A to C, I'm going to have to take that integral from that portion, from A to C, and put a negative sign in front of the integral. So it will end up being a positive value. Remember, the integral, because it's underneath, will turn out negative, and the negative in front will negate the negative, and we'll have a positive. The integral from C to D is all above the axis. So we don't have to mess with that, just add it on. And then from B to B, from here to here, we have the negative again. So I'm going to have to put a negative out in front and change the sign so that it gives me the area being positive in all respects. So that's the theory. So I want to add another, and I've kind of alluded to that. I'm not sure it's come up exactly the way I hoped it had. So we're going to practice some of this, but we're going to practice it by adding another layer. So what's happening in the layer that I'm going to put on top of this is I'm going to call this function, instead of f of x, I'm going to call this function the velocity function. And do you recall in physics what the area under a velocity curve is? It turns out, like I think I presented it way back in physics, like suppose that the velocity was constant. And say the velocity was constant at 3. And it say the velocity is 3 miles per hour and it went for 2 hours. So 1 hour, 2 hours. So it turns out that the area under this curve, I can tell what that is. It's a 3 by 2, so it's 6, but 6 what? And it turns out we have 3 miles over hours times, then we took this dimension, and it was not drawn to scale, which is fine. Alright, so 3 miles per hour times 2 hours. And the unit, hours, cancel and it leaves miles. Did you remember that the area under velocity curve is distance? Well, it is. So we're going to put a layer of meaning. So not only are we going to find the area between the curve and the x-axis, we're going to call it a velocity curve. And I'm going to ask you for 2 things. Displacement and the distance traveled. Alright, one of these is going to ask you to use a straight integral, and the other one's going to ask you to divide up the integral so that every portion is positive. So let's go ahead and do one, and you'll see what I mean. The one I want to do, and I don't know that I'm going to do it every little step, but enough that you get the theory. I'm going to give you the velocity of a object, and velocity at any time t is t cubed minus 10t squared minus 29t minus 20. Alright. If you graph that, you would find that the graph is an expression that starts at, say we look at it from 1 to 3. No, I'm sorry, from 1 to 5. 5. So it's going to start out, it's going to go up, and it's going to come down, and then back up. So you can see areas between this graph and different portions between the graph and the x-axis. So what we're going to do is the first question is going to be find displacement. Once again, back in physics class, in Mod 1 or 2, or somewhere in physics class, you learned how displacement is relating to distance. And displacement actually gives you the position where the object is. So if an object starts at a certain place at time equals 0, putting in a time equals 0, we would know that it would start there, and then it would go in the positive direction, whatever this area is. So it would start in one spot and go a certain distance to the right. And then this little distance goes below the x-axis. It's a negative distance. So in displacement, what will happen? It'll come back a little bit. So when we're asked for displacement, you can see that the integral can be conducted all the way from the first to the last spot. So 1 to 5 of t cubed minus 10t squared minus 29t minus 20. So we're going to take all of that, dt, find the areas mentioned, and the integral will do all the work of adding and subtracting the way we want it to for displacement. So we're going to get t to the 4th over 4 minus 20t to the 3rd over 3 minus 29t squared over 2 minus 20t. So all of that is going to be evaluated first at 5 and then subtracting it at 1. And when we do all that, we're going to come out with a value. I think it was 71 over 6 feet. Alright, as I said, I wasn't going to do all the nitty-gritty work. We're just working on theory here. So that's what you would do when you find displacement. Alright, let's talk about perhaps the more interesting, let's look at the distance traveled. Alright, so here's displacement. Alright, we'll leave the graph up there. Same equation. Now instead of displacement, I'm going to ask for find total distance traveled. Alright, distance traveled is sort of like area under the curve. It's always positive. So therefore, even though we're going in one direction in this area, we're going in a different direction. It's still going to be out as a positive value, and we're looking at total distance traveled. Total distance traveled does not care about the sign or the direction. It just means distance traveled. So let's say that this actually crosses the x-axis at 4, and I do believe it does. So drawing that a little clearer. All right. This function comes down and crosses the x-axis at 4 and bends and goes back up at 5. So the points of interest on this curve are 1, 4, and 5. Now this time I want this area as a positive number added to this area as a positive number. So I'm going to take the integral from 1 to 4, which is all above the x-axis, of t cubed minus 10t squared minus 29t minus 20 dt. And then when I get to the part that goes under, the integral, the raw integral, will calculate that as negative, but I want it as positive. So I'm going to put a negative in front of that integral, that section from 4 to 5. Of t cubed minus 10t squared minus 29t minus 20 dt. Alright, so I'm going to take the integral, so a little bit of legwork. I'm going to take the integral of this, which I aforesaid mentioned, and then evaluate it at 4 minus at 1. And then I'm going to do the same thing with this integral, evaluate it at 5 minus 4, but I'm going to subtract that value from the original. If I did all that, it turns out that the total displacement, this total distance traveled is I have 32 over 3. I think I might have exchanged those two answers, 32 over 3. So I think maybe that's the 71 over 6, because 32 over 3 is going to be 64 over 6. So that's the smaller answer, and I'm expecting the larger. All right, I took notes in haste. If you would then, erase the answer that I gave you to the one where it talked about total displacement and put in 32 over 3. And the answer to this one is the 71 over 6. All right, if that's not the case, I'll look at it closer. But if that's not the case, I'll alert you tomorrow. All right, so this is how we're going to work with area between a curve and the x-axis and layering on a little more meaning as we go. All right. Talk to you tomorrow. Hope that you are having a good evening. Over and out.